It's starting. Sometimes it takes a while, I don't know, to start. Hola a todos, ¿qué tal? Bienvenidos al seminario de Álgebra. El día de hoy nos va a hablar Tom Meyerovitch, que trabaja en Israel. So, thank you very much, Tom. He's going to talk to us about invariant random orders on groups. So, thank you very much, Tom, and please.
Okay, so thanks Alonso for the introduction and for the opportunity, and thank you all for coming. So the subject of my talk today is orders on group, and in particular invariant random orders. And I will explain what this means and how it's connected. Now, I should mention up front, this is based on joint work with two colleagues of mine. So Yair Glasner, who's also a professor at Ben-Gurion University, my department, and Yuqing Franklin, who is currently a postdoc at Texas A&M, and he was a postdoc at Ben-Gurion University when this project started. Okay, so he didn't work, and he left back to A&M at the beginning of this year. Okay, so for introduction, and I'm not, this is an algebra seminar, but I'm not completely sure of the background of the audience, so feel free to interrupt me if you're familiar with whatever I'm speaking, or stop me and ask for explanations if I'm going too fast about something. That's it. So I'll begin with the background. So about orders on group. Okay, invariant orders on group. So if you have a countable group, it's a set, and an order, okay, on a set or in a group, it's just a relation, a binary relation, which is reflexive, transitive, and antisymmetric. Okay, that means that any element of the group is less than or equal to itself. If x less than or equal to y and y less than or equal to z, then x less than or equal to z. And antisymmetric means that the only way that x can be less than y and y less than or equal to x is if x is equal to y. Okay. Now, a total order. Okay, this is a partial order. A total order means that any two elements, either one is less than the other, or the other is less than, one is less than or equal to the other. There's only, it's a total order, or sometimes it's called a linear order. Now, if you have a group, then in addition to order, you have the group action, the group multiplication. And saying that an order is left invariant means that multiplying both sides of the equation from the left by an element of the group, respects the order. Okay, so the usual order.
So, sorry, Tom. I think I don't know if you're changing the slides, but we still see the same slide.
No. Okay, no, right. Yes, sorry. Yes, all right. Okay, sorry about that. Yeah. So I was just reviewing the the properties of an invariant order. So invariant order is a relation which is reflexive, transitive, antisymmetric. And the invariance property means that multiplying both sides of the equation by an element of the group does not, respect the order. Okay, so this is a left. If the group is not commutative, you can talk about left invariant orders or right invariant orders, which means that multiplying from the right respects the order. And bi-invariant order means that multiplying from the left and from the right keeps it the same. Okay, so the usual order, for example, on the real numbers or the rationals or whatever, as an additive group is an invariant order. That's kind of the simplest, most basic examples, or on the group of Z of integers. Now, in general, okay, let me go to slide 3. In general, okay, there's a
sorry again. At least I think we see the same slide for some reason. So maybe you can kind of stop the sharing and share it again.
Let me understand. Yeah. For example, what's going on. Why is this? Okay, I see now. I had two copies of the window open.
Right. Okay, great. Now we see it moving.
Okay. Now I see what's going on.
Okay, great. Thank you.
Very briefly. Right. So, okay. Very briefly, invariant order. And the next thing I wanted to say is that there is a bijection between invariant partial orders on the group gamma, left invariant partial orders, and semigroups of gamma that do not contain the identity. Now, how does this bijection go? You just, given an invariant random order, the set of elements which are less than the identity, according to this order, is a semigroup. Okay, because if something, by transitivity, if one is less than the identity and something else is less than that, then it's also less than the identity. Okay, so it's closed under composition. It does not contain the identity, the things that are less than the identity, and that's it. The other way around, if you have a semigroup which does not contain the identity, then you can define, okay, so the bijection goes like G is less than H if and only if G minus 1 H is in the semigroup. Okay, so this is the bijection. Given a semigroup that does not contain the identity, you can define a partial order this way, which will be invariant. Now, you can ask which semigroups that do not contain the identity corresponds to invariant total orders. Okay, that's what I wanted to say, total orders. And the answer is that they should have the additional property, what's called an algebraic path. This means that, okay, it's a semigroup, it does not contain the identity, and any element of the group is either in the semigroup, its inverse is in the semigroup, or it's equal to the identity. Okay, is that clear? If you have a semigroup which does not contain the identity, it has the property that it's maximal in this sense. Okay, any element is either in the semigroup or in the inverse, then the corresponding invariant order is total order. Now, an example for that is, of course, okay, you can talk about, you can look at the group Z, the group of integers, and the natural numbers are a semigroup that does not contain the identity, and they are an algebraic path. That's the simplest example. And you can generalize this to ZD, to torsion-free finitely generated abelian groups as follows. You can take the what's called the lexicographical order. So here it is illustrated. If I look at all the coordinates, or all the elements of Z squared, for example, where either the Y coordinate is positive or the Y coordinate is equal to 0 and the X coordinate is positive. Okay, this would be a lexicograph. Compare points lexicographically, both first according to the Y and then according to the X. You could do, of course, the other thing. Then okay, the red points, they are a semigroup and they are an algebraic path. The inverses are precisely, the bottom, the thing I'm illustrating in blue now. Okay, so every point in Z squared is either in the blue, the red, or it's the origin. So this is kind of a typical example. These are invariant orders. And actually on ZD, okay, of course, left invariant and bi-invariant is the same because it's an abelian group. And you can actually, there's actually characterization of what the invariant total orders are. And they somehow correspond to half planes. So this is kind of correspond to a half plane with slope 0. Rational half-planes are kind of the same. You have to partition, and there's also an irrational half-plane. You can look at all the points. You can take an irrational vector in non-zero vector in irrational direction, okay, in R2, okay, or on the sphere, and then you can compare 2 points by taking the inner product with this direction. This would give you a total. And that's it. These are all of them. Okay. So the groups that admit a left invariant total order are called left-orderable groups. And not every group is left-orderable. Okay, some example for groups that are, okay, abelian groups are left-orderable. I sort of indicated why. So by abelian groups, actually I have to be torsion-free abelian groups, right? Of course. And more generally than that, torsion-free locally nilpotent groups have this property. So a group is locally something if locally P if every finitely generated subgroup has this property. And there's some general argument that says that if every finitely generated subgroup of a group is orderable, then the group itself is orderable. Being orderable is a local property. Another fundamental result in this area, kind of a classical result, is that free groups are orderable. And this is slightly trickier to see, but there's some arguments for that. I will explain it in a moment. So free groups are orderable, torsion-free groups are orderable. Now there are various groups which are not orderable, and it's tricky to find what is what sometimes. So there are kind of trivial reasons for what the group would not be orderable. For example, finite groups are not orderable for an obvious reason, and the reason is that an order on a finite set would have a maximal element, and this maximal element should be invariant under multiplication, which is impossible, right? So the only finite group which is orderable actually is the trivial group, if you consider this to be a group. And more generally, if a group is orderable, then every subgroup is orderable, because the restriction of the order to the subgroup is still a total order, right? It's still invariant. It's invariant to the big group. So therefore, groups that have finite subgroups are not orderable. In other words, if it has torsion elements, okay, this is equivalent. Now, so these are sort of the trivial reasons. And then there are many, many more complicated obstructions for orderability. So for example, the group SL and Z, well, it's never orderable because there are fine elements because there's torsion, but you can avoid this problem by going to a finite index subgroup, and for n greater or equal to 3, finite index subgroup of SL3Z, sorry, are non-orderable. And I will kind of get back to the sketch of this argument. This is a result due to David Whit-Morris from about a decade ago. And there's a recent kind of breakthrough sort of result by Otando and Deroin that generalizes this and says that the higher rank lattices are also non-orderable. Now, the interest in this is because orderability of groups has a relation to many areas of mathematics. Okay, so for example, this is an easy argument that orderable groups satisfy one of Polanski's conjectures, and orderability can be expressed in terms of acting faithfully on the real line by order-preserving homeomorphisms. It's related to the Zimmer program, etc. So the upshot of this is that it's there are non-trivial obstructions for when a group is orderable or not, and it's a complicated issue. Now, a fruitful point of view from related to dynamics and topology from this is to consider the space of orders on the group, or more commonly, the space of invariant orders of the group, but this is a subspace of the space I'm considering. So an order on the group is a relation. You can think about it as an element of 0, 1 to the gamma cos gamma. Okay, this is the space of binary relations you identify on gamma. Within it, the conditions of being reflexive, transitive, and antisymmetric, these are conditions that are closed in the topology. So the space, which are denoted by ord gamma, where gamma is the countable group, is a compact subspace of the space of binary relations. And there's gamma acts on this space. Now, it acts on it in two different ways. It acts by multiplication from the left and also by multiplication from the right. Now, if you want it to be a left action, then the multiplication from the left has to be by the inverse. That's the usual kind of thing. So there's actually an action of gamma cross gamma on the set of orders on gamma. And to be more specific, there's an action of gamma cross gamma modulo the center. It factors through the elements of the center embedded diagonally, the center of gamma embedded diagonally act trivially. So is this clear? Is this any questions about this? Okay, so now let me introduce. Okay. So now let me introduce the main notion that I'm going to discuss here. The title of the talk. These are invariant random orders. I'm defining it. So an invariant random order, it's a probability measure, or you can think about it, if you're a probabilist, you can think about it as a random variable taking space, taking values in the set of orders on the group. It's a random variable. Okay, and it does not take this values in invariant orders, but the distribution, okay, or in other words, the measure is invariant with respect to multiplication from the left. Okay, so it's a probability measure, it's a random object, and I need to explain that this kind of philosophy of taking some algebraic or deterministic object and formulating a random version of it, and okay, if you had the deterministic object related to a group, then you take the invariant random version of it. This is kind of fruitful in many areas, and one very famous place is the notion of invariant random subgroup. It actually turns out to be connected. This was its classical notion. Well, actually, it's a notion that's kind of very fruitful nowadays. The name was introduced in the paper about a decade ago by Albert, Virag, and Glasner, sorry. Yair Glasner, my colleague. And so invariant random subgroup is a group. It's a probability measure on the subgroups of a given group, such that the measure, okay, or distribution of the random group is invariant under conjugation. So it's kind of analogous. So the invariant random order, it's a generalization of the notion of just an invariant, left invariant order. And the reason is the following. A left invariant order, you can associate the probability measure, which is constant, it's a delta on this point. Okay, it's a deterministic, it's random, but it's deterministic. With probability 1, you get this particular order. And because the point is invariant, the distribution is invariant. So it's really a generalization of the usual notion of invariant order. Is this clear? It's clear. I hope so. Okay, now let me just illustrate this by an example. And this example will say something more than that. It will say that in contrast to invariant orders and deterministic invariant total orders, every countable group admits a random, an invariant random total order. And here is one specific one, and this is an older observation, but it was quite useful. And it was used at least in the mid-70s in applications for entropy theory by Kiefer, and apparently around the same time by Stjepin. So this is what I'm going to describe is called the uniform random order. So you have any countable group gamma. So there exists a unique probability measure on the set of orders that satisfies the following property. Take any distinct n tuple of distinct elements in the group and any permutation of them. The probability that you choose an order that restricts to this permutation is 1 over n factorial. In other words, it's the same for any permutation. Okay, any 3 elements, there's equal probability that the first is bigger than the second, bigger than the third, as any other permutation. Okay, so the definition of the order, I mean, the property of the order is clear?
Yeah. Thank you.
So the reason that it's invariant under left multiplication, well, it's also invariant under right multiplication. It's in fact invariant under any permutation of the elements of the group, right? It's the reason that it's well defined. Okay, so one way to see it from this way it's expressed, you can kind of think about it in terms of this. It's called the Kolmogorov's consistency here. It says that if you have probability measures, you know, increasing marginals, and they're consistent, then there's actually a random variable that satisfies them jointly. Another way to see it, to realize it, and this is important for what I'm about to say again, to think of how do you realize this uniform random order? You can take your elements of the group, and for each one of them, choose uniformly at random, independently, a random variable between 0 and 1, okay, and the interval 0, 1, according to the Lebesgue measure. Now, with probability, and then you define the order according to, you compare 2 elements according to the random variables you chose to them. Now, with probability 1, no 2 of them will have the same value, so you get a total order, and it's kind of straightforward to check that the distribution will satisfy this property. So
sorry, just one question about that. There's the group. It doesn't have to satisfy anything else. Can it be even a finite group? Can it have torsion?
Yeah, so exactly. So this is, yeah, we said countable, but by countable I meant countable or finite. Well, you know, it's if you think about groups that are not countable, then you run into problems of measure theoretic nature. It's not a standard probability space, but it's not a big issue. But finite or countable groups, yes, it works the same. For finite groups, this is kind of trivial to define. You just, you know, do a random permutation of the elements, and that's the order.
Okay, thanks.
Okay, so this is kind of a straightforward example, but what it shows is that, you know, there's no notion of random orderability for a group. All groups are randomly ordered. They admit a random invariant order. And in fact, much more you can say, and this is what I'm saying now, there are many, many invariant random total orders. And here are 2 manifestations of this phenomenon. One of them that we were able to prove is that if you take any ergodic essentially free probability preserving action, okay, an abstract action of your group, then you can realize it as an invariant random order in the following sense: there exists a probability measure on the space of orders on the group, of total orders on the group, which is invariant under the group action, and such that in the ergodic theoretic sense, the probability preserving system on the space of orders is isomorphic to the one you started with. Okay, and so, you know, like there are many different kinds of measure preserving actions of the group Z or Z squared or the free groups, many free actions. Each of them, you know, corresponds in some way to at least one invariant random order. Okay, that's one way to show that there are many of them. Another type of phenomena that shows the richness and also in some sense how the space of random invariant orders, the IRO gamma, this is the space of invariant random orders, gamma, reflects the structure of the groups, is this result that we were able to prove, mimicking the Glasner-Weiss dichotomy. So this Glasner is Eli Glasner, the father of Yair Glasner, my co-author, different Glasner, but so Glasner and Weiss, Glasner is the father, and Weiss proved the following well-known tracking theorem. If you look at the invariant, you have a countable group, and you look at the invariant probability measures on A to the gamma, where A is a finite set, then there can be two, or actually compact set, there can be two possibilities. If your group gamma has Kashdan's property T, then the ergodic measures, the extreme points of the simplex of invariant measures, they are a closed subset if you have property T. And this is what's called a Bauer simplex. A Bauer simplex is a closed Choquet simplex. It's a Choquet simplex where the extreme points are a closed subset. Like, you know, what we're used to, finite dimensional simplex. You look at the, you know, the usual simplex in R2 or R3, okay? The extreme points, they are on the boundary, they are a closed subset. If your group gamma does not have property T, okay, so for example, amenable groups, infinite amenable groups, Z squared, free groups, etc., then the extreme points are dense. Now, this is kind of strange. You think of it, it's kind of, you have a simplex, and the points which are extreme, they're dense. Their closure is everything. It's the opposite. And this is, by itself, it's a kind of a strange object. There's no, it's a classical object in analysis, and it's known to be unique. Okay, there's a unique compact simplex which has dense extreme point. It's called the de-Poulson simplex. So what we were able to show is that the IRO, the invariant random orders of gamma, which is also a simplex, it's a closed, it's a compact convex subset, okay, on which gamma acts. It also satisfies the same dichotomy. Okay, so these are two results that show that there are many, in some sense, invariant random orders. Well, at least the second result shows this in the case that the group does not have property T. Property T groups include finite groups, and in that case, you can exactly know what the simplex is. It has the extreme points, they correspond to an order, you know, just a permutation of your group up to cyclic permutation. So there are n-1 factorial extreme points on a group order. Now, here's the question I'd like to address the rest of this talk, and this is the question of extensions of orders. Okay, and here, let me phrase the question. The question has a classical counterpart for deterministic orders. So the question is, given a partial order on gamma, let's say it's invariant, when can be extended to an invariant total order? And here I'm adding the word random. This is the new version. Okay, so obviously, if the partial order was not invariant, it cannot be extended to an invariant total order. That's obvious, because, but, well, okay, it's not completely true, but let's say you started with something which is invariant. Can it be extended to something which is invariant? And the answer turns out to be quite complicated in the deterministic case. There are various examples on all kinds of groups which are okay. A necessary condition is, of course, that the group be left-orderable, because if it's not left-orderable, then you cannot extend any. There does not exist an invariant total order. But even if your group is orderable, left-orderable, you're not necessarily guaranteed to extend. So there are examples, kind of sporadic examples, not of groups which are nice. I mean, there's a torsion-free solvable example of a group which has some semi-group not containing the identity. So this corresponds to a partial order, which is left invariant, and it cannot be extended to an algebraic past, and or in, by this bijection to an invariant total order. But in some cases, for example, if your group gamma is torsion-free and locally nilpotent, as explained, then I indicated before that these groups are orderable, and moreover, if you started with a partial order, which is left invariant, you can extend it to a total order. Okay, and it's pretty much, so it's worked for this class, but if you go a little bit beyond from locally nilpotent to solvable, for example, then it fails. And not because of lack of orderability. So that's something very subtle about deterministic orders. On the other hand, for random orders, you have a soft substitute for that. And it's quite easy, but we applied this in the previous paper with two of my colleagues, Andrea Alpiv and Yair. Now, the result is probably known before. Apparently, it appeared in a paper of Yuqing also from the, but I've just learned this from the 70s in some form, maybe. And the proposition says that if you have a partial invariant order, possibly random, okay, this is just generalizing, it can be, and your group is amenable, then it can be extended to invariant random total order. I will indicate later on what this proposition, the proof of it, it's more an observation. It's more or less immediate. I can indicate it, for people used with the definition of amenability. And the reason is that given a partial order, invariant partial order, the set of total orders extending it, which is non-empty, you can just extend it in an arbitrary way, this is a compact subspace, and gamma acts on this subspace. So any compact gamma space for an amenable group gamma admits an invariant probability measure. And this probability measure would be an invariant total order. That's it. That's the proof. Now, this proof used in an essential way the property of amenability. It can be expressed in different ways. There are various formulations of amenability. There are alternatives to this short proof, but they all use amenability somehow. And the question is, okay, it's clear that the proof uses amenability, but is the proposition, could it possibly be true without this word amenable? This is a question we posed in this paper, and we were not able to solve it, based on abstract considerations at the time. I mean, at some point we felt, maybe there's a slightly different technique that can do it beyond the amenable case or something. And the result, which I'm going to describe for the rest of this talk, is that the answer is no. Okay, you cannot just remove this amenability condition here. So this was what we were able to now resolve with Yair, Glasner, and Frank Lin. And it follows from this theorem. Okay, so the example, we've looked at various examples, and the one we were able to find, it was based on specific considerations. It's not, I mean, it might not be the most general result, but that's what we know at the moment. On the group SL3Z, there is a fixed and very natural partial order, which cannot be extended to an invariant random order. Now, this partial order is just defined by, a matrix is bigger than the identity. The SL3Z is the group of 3x3 matrices with integer entries and determinant 1.
Sorry, Tom. Again, the slide I think didn't change.
Oh, I'm sorry.
Maybe the get that makes.
Okay, thank you. So here is the statement of the theorem. I'm saying that the group SL3Z, this is the group of 3x3 matrices with integer entries and determinant 1. Okay, inverted. Okay, yeah, and write the orientation preserving automorphisms of the lattice of Z3. So on that, you have a partial order defined by, it corresponds to the semigroup generated by, so I didn't say whenever, right, I didn't say here whenever A has no negative entries. Okay, so this is a partial order. Of course, you cannot define. I mean, there can be two matrices. You have a matrix A and a matrix B. How do you know which is bigger than the other? You take the inverse of A multiplied by B. If this has no negative entries, then it means that A is smaller than B. Now, it could be that the two matrices are incomparable. It's a partial order, but it's invariant, of course. Okay, I'm describing it I'm describing the semigroup. And the idea of the proof, it comes from a result of Dave Whitmorris that I indicated before, around a decade ago, that where he proved, the paper has various results, but this particular part says that finite index subgroups of SL3Z are not orderable. Non-orderability of SL3Z, essentially, but not based on the trivial fact that it has torsion elements. Okay, so that's what I would like to explain. And the proof, it amounts to a combination of two ideas. One of them is kind of the essential idea in Dave Morris's proof, which is it's based on an analysis of the algebra of SL3Z. It's algebraic manipulations and algebraic manipulations. And the other thing is the notion of wandering sets or recurrence. So let me explain the idea. So we let less than subscript 0 be the partial order that we want to extend. This is A is less than or equal to B if and only if A minus 1B has no negative entries. That's what I described. And A and B are elements of SL3Z, which I'll denote by gamma for short. And let me denote by X this partial order, the extension of this partial order. You can do this in general. This is the set of total orders on the group that extend this partial order. Okay, and what we want to prove is that there is no random invariant order extending this. Okay, which, in other words, means that this space, which you can check is a compact gamma invariant space, does not admit a probability measure, which is invariant to gamma.
So sorry, Tom. Again, I think you're in the next slide again.
Okay. Yes. Sorry. Yeah, you will have to remind me. Yeah. Okay. So. Okay. So again, the overview of the group. I am denoting the partial order which I want to extend by less than 0. Okay, it's defined this way. No negative entries. I'm denoting by x gamma less than or equal the set of total orders that extend this particular one, and our job is to show that this space x gamma less than 0 does not support a gamma invariant probability measure. That's the restatement of the theorem that we want to prove. Clear. This is equivalent to saying that there is no invariant random order extending this partial order. And how do you show? Okay, now I should indicate at this moment it's not the easiest way or whatever. This, of course, will show, okay, either by the observation before or by the other, that that SL3Z is not amenable, okay, which is a well-known fact. But it has to somehow take this into account. Non-amenability of SL3Z has to come into the proof, right? It has to be. It's a you either have to, and we will not assume it. We will kind of do something direct, which will be based on it. And so we have to look at the structure of SL3Z, and here is the structure. So what I'm about to say is I want to describe a set of generators for SL3Z, which also generate, which will be in the semigroup corresponding to the partial order and will generate it. So the semigroup corresponding to this partial order is generated by the 6 basic unipotents in SL3Z. So these are the 3x3 matrices which have exactly one off-diagonal entry, which is non-zero and it's equal to 1. Okay, it's either 1 here, 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 right? There are 9 entries in 3x3 matrices. 3 of them are the diagonal. I will force them to be 1. And there are 6 options for off-diagonal settings, so I'm ordering them kind of in a counter, well, not exactly in a particular order, okay, going like this, right? And these generate SL3Z. And there's also, okay, I'm about to describe actually a presentation of SL3Z, and the relations between these things are the following. If I take 2 consecutive indices, and here I'm taking the indices modulo 6, so like 6 plus 1 is 1. Okay, 6 is equal to 0. So AI plus 1 commute. Okay, here I'm denoting here the commutator. It means multiplying AI by AI plus 1 is the same as multiplying AI plus 1 by AI. Okay, it's a commutator in the group theoretic sense, not in the ring sense. And if you take 2 elements of distance 2, okay, then the commutator is whatever in between. It means if you take 3 consecutive indices, that's the conclusion from that, then the group generated by them is isomorphic to the discrete Heisenberg group. Okay, so this is a kind of the basic classical fact about SL3Z. It's a key ingredient in many of the proofs of the results for SL3Z. Is that clear? So it takes, if it's the first time you've seen it, it takes a little time to verify, but verification is no more than multiplying matrices. It's an exercise. It also has geometric meaning, intuition. But if you're used to it, it's completely standard. If not, it takes some time to simulate or not to this time. So this is what I'm going to use. And now there are 2 parts to this proof. The first part is kind of really mimicking what Dave Morris did in a specific setting. He was just looking at the invariant orders, and you want to show that there are none. So I consider this subset of the orders that extend my partial order. I'm looking at I'm denoting, I take A and B, they're elements of gamma. I will take later A and B to be one of those basic matrices from the previous slide, and one of these matrices, right? The A and B will denote these, but definition can be in general. So S plus AB is the matrices where there exists some Q, such that for every n, A to the minus Q, B to the n is less than the identity. So this in some sense means that Q is that B is much less than A, okay, in an imprecise way, right? Because you take B to the 1 million, there's a specific Q, maybe Q equals 10, such B to the, right, if it was invariant, if you can multiply both things by A to the Q, then it would mean that every power of B is less than A to the 10. So in some sense. And then there's an analogous notion, A minus, which also says in some sense that Q is much bigger than, A is much bigger than B. Okay, so these two sets are various ways to indicate that A is much bigger than B. And if you intersect them with invariant orders, they're the same. There's just one order. This is the lexicographic order. If A and B commute, there's just precisely one order that in these two sets, one invariant order in these two sets. Now, the basic lemma, by some iteration and using the basic relations that I indicated here, the basic result says that any element of the extension is either in the intersection of AI plus 1 for I equals 1 to 6. So in other words, in some sense, A1 is much bigger than A2, A2 is much bigger than A3, A3 is much bigger than A4, A4 is much bigger than A5, and A5 is much bigger than A6, and A6 is much bigger than A1, so a circular kind of thing. Or the other way around, A2 is much less than A1, A3 is much less than A2, etc., much less in this informal sense. Now, this is purely algebra. It's based on a geometric notion. And the notion is the following, right? If you take every three consecutive elements, they generate a group which is isomorph of the AIs, right? AI, A1, A2, A3, for example. They generate a group isomorphic to the Heisenberg group. So you can draw, right, to the Heisenberg group. I'm showing the picture here. And the Heisenberg group, the element, you can kind of think of it as Z3, right? You can draw it in coordinate of Z3, but the geometry is somehow skewed when you multiply it. So for an element of the Heisenberg group, I would have this shape are things that are, for any element of the extension, they would be bigger than it. Now, the geometry of the Heisenberg group works that, when you translate by something, you're shearing one of the dimensions. So if I take this point and move it over here, this quadrant, which was, this quadrant, which was straight here, will be sheared, sort of. And based on this geometry, or you can just do it directly by algebra, you can see that, if something is, you can see that, if these elements are bigger than the identity, then you can go up here, right? And then multiply by elements that are bigger and see that this is also much bigger. Okay, this is kind of a geometric illustration of this fact. Okay, you kind of iterate. It has to do with Heisenberg geometry or Heisenberg algebra, iterated. Now, this lemma by itself was sufficient for Dave Whitmore to conclude the proof, because by invariance. Okay, it's impossible to have 6 elements for which the first is bigger than the second is bigger than the third, and so on, and the sixth is less than, the first is again bigger than the sixth, right? It's not possible for an order. It contradicts antisymmetry and transitivity. But in our setting, there's no invariance, so there's no kind of transitivity for these relations. And it's not true that this intersection is empty, but, and this is the punchline, the punchline is that these intersections, although not empty, they are small enough so that they cannot support invariant probability measures. And how do you express this precisely? So they are countable unions of wandering sets with respect to the action of gamma. So what is a wandering set? I will explain, and I will conclude with that, more or less. So if gamma acts on X, and A is a subset of X, A is called wandering or weakly wandering if there exists G in gamma and N1 and 2. Okay, if there exists G in, just wondering, let me say the easy definition. Such that there exists G in gamma such that A, G to the A, G squared to the A are pairwise disjoint. Okay, now if you have a wandering set, then with respect to any invariant probability measure, it must have measure 0. The reason is that if the measure is invariant, all these must have equal measure, but they have to sum up to 1. You can't have infinitely many things that are equal and they sum up to 1. Sorry, sum up to less than or equal to 1. If they sum up to less than or equal to 1, they must all be 0, right? I mean, if there was something positive, then they would sum up to infinity. So a wandering set has 0 measure with respect to any invariant probability measure. Countable union of wandering sets also has measure 0 with respect to any invariant probability measure. We show that this and this are countable unions of wandering sets. Therefore, X gamma 0 is a countable union of wandering sets. Therefore, it cannot support an invariant probability measure. That's the basic argument. Now, I see that my time is almost over, so I will maybe leave time for questions if you have. And if you're interested, I have some questions. But
thank you very much, Tom. Thank you. So yes, you can ask questions now. Si quieren pueden escribirlas en el chat o pueden hablar directamente y les puedo ayudar, o pueden preguntarse en inglés como ustedes quieran. So I just have a question about this last part. So where is exactly the point that is non-amenable? Is it that in the wandering sets, or?
Yeah. So if you have a compact, if your group acts on a compact space, and the compact space does not admit an invariant probability measure, then this shows that the group is non-amenable.
Okay. All right. Okay.
Right.
Sure. But it's by one of the definitions. Sure. Right.
Yeah. So. Yeah.
Okay.
Any proof of non-amenability of well, of course, there are easier groups because SL3Z contains, for example, free groups, etc. There are easier proofs that it's non-amenable, but this somehow reveals it. It shows much more.
Mm-hmm. Okay, great. Thanks. But by the way, there's a question here in the chat by Miguel.
Yeah, okay, wait a second. Let me just, I'm not used to...
So yeah, I can read it for you.
Yeah, but wait a second. I can probably find it. The chat. I see the chat. Yes, right. Okay. Yeah, I see. Okay, so the question is, when we want to build an autophorism with a Z full shift, we can do it by the marker construction. Headland. Do you know if this construction is possible for a bi-orderable countable group? This is a good question. I actually have not thought about. I mean, I'm not familiar with result that use orderability of a group
for the marker construction.
Yeah, which is I mean, the left invariant orders are compatible with the shift. That's the point. So in that sense, it's well, actually, that's not completely true. There are some results, some recent results about, for example, algebraic group actions or algebraic shifts that hold for a family of groups, and in particular for left-orderable groups, but the reason is sort of indirect. It's due to the fact that left-orderable groups satisfy something called the strong Atiyah conjecture. So I'm not. I don't know. I mean, left invariant orders are very useful for many applications. It could be, and random orders also. I'm not familiar with. Well, no, actually, that's not true. Actually, you might want to look at. I think Romundo Ochino. How did you say you pronounce his last name?
Briseño.
Yes, a paper involving something about orderable groups and subshifts with strong spatial mixing property. It might be related to this question, but I have not thought about this question. I don't have a kind of off-the-shelf answer for this.
Great, thanks. So let me see. Any other question? ¿Alguna otra pregunta? So, I don't know if this was. Yeah, Alejandro.
I just make a question about the theorem of the uniform order construction.
Of the what? Sorry, about the
theorem that say the countable group, that theorem.
Yeah, the second one or the first, the dichotomy?
The first one, that theorem.
This one, right?
Yeah, this one. No, the first one.
The realization, right? The realization theory. Yeah.
Well,
or the
for
example,
the example of the uniform random order, I have a question about the integers with the usual order. I think this is not the order what.
No. The integers with the usual order is invariant. And this corresponds, so I mean, the system corresponding to it will be a system of 1 point. This would be the trivial action on 1 point.
Oh, they are trivial. Okay.
Right? There's nothing going on. But so this is a completely different orders, right? I mean,
completely different. Okay. But there exists only one, a unique order for.
No. I mean, there are many invariant random orders. There's a unique one which is called the uniform random order.
Yeah, the uniform random order.
This is a specific point. I mean, from the ergodic point of view, it's isomorphic to an infinite entropy Bernoulli shift, it turns out.
Okay.
It's not so difficult to see this.
Okay. I'm gonna think about it. Thank you.
Okay. Any other question? Okay, so we thank Tom. Thank you very much, Tom, for very interesting talk.
Okay,
So,
thank you very much. Thank you for the questions. And,
thank you. Thank you. So, great. I will send you the link of your talk, and thank you very much. So, I think we can download also the slides here in the link you send us, right?
yes, the
Yes.
slides are available. Yeah.
Yeah.
If you have any questions, comments, these results, they're currently in writing. I think hopefully we'll have a preprint uploaded soon, but
great.
what exactly soon is it's random, but it's in the future. That's for sure.
Okay, we look forward.
It's after this talk, that's I'm sure.
Thank you.
Okay.
Thank you very much. Okay.
Bye.
Bye. Thank you. Hasta luego. Hasta luego a todos.
Thank you. Gracias.
Adiós.
Alonso.
Sí, gracias a ti. Hasta luego, Alejandro. Gracias. Adiós.